Thank you. Thanks for the introduction. Hi, everyone. I'm Mate, and this is joint work together with Kuldeep Meel. The title is Gaussian Elimination meets maximum satisfiability. The motivation for our work were two challenge instance types. One is network reliability, where we model a power grid as a vertex-edge graph and compute the probability that 2 points S and T are connected. And this can be reduced to discrete integration. And the other problem or challenge instance type is partial function computation for partition function computation, for spin glass model. And this is a fundamental problem in particle physics, where the spin glass is a magnetic state characterized by randomness, and variables represent spins, like +1 and -1, and spin variables have 4 neighbors. We use the 7x7 spin glass model as per previous work. And both of these instance types can be solved with partial weighted MaxSAT solving that has hard XOR constraints. So now the challenge was how to put together a MaxSAT solver that can efficiently handle XOR constraints that are hard, so they're not soft constraints. So what is the partial weighted MaxSAT? Well, it's CNF, but has hard constraints and that cannot be violated, and soft constraints that can be violated, but with a cost attached. And the goal is to satisfy all the hard constraints and minimize the cost violation of soft constraints. Next up is Gauss-Jordan Elimination, which obviously deals with hard XOR constraints. So these XOR constraints are, of course, linear equations over the Galois field of 2. And this is a classical algorithm that you might have also heard of in high school. So it's ortho n cube with a naive implementation. And there are optimized algorithms that exist that push this down more towards the ortho n squared, but they focus solving Gauss-Jordan Elimination once. And as you will see, that's not exactly what we'll need. So the way that we plug things like this MaxSAT solver and the Gauss-Jordan Elimination solver together into a cohesive whole is what has been called before DPLLT, and I think the more relevant way of calling this is CDCLT. So basically, we have a CDCL solver and the theory solver that work together to solve a problem that neither of them can solve on its own. And so in this graphic that you see on the screen, the CDCL solver is on the left, and it takes in the CNF constraints. And the theory solver is on the right and takes, of course, the theory constraints. In our case, will be XOR closes. And there is an API between the two where the CDCL solver provides the current assignment stack and the current set of conflict closes to the theory solver. And the theory solver, in part, will give new propagations, new conflicts, and the reason close for these new propagations and conflicts in the CDCL solver. So this is the way they work together. And CDCL with Gauss-Jordan Elimination, the way they work, well, the way this system works together is at the top level, the equations are never full rank in the matrix. So there are too many variables, too few equations, and Gauss-Jordan Elimination basically does nothing. But as variables get branched on and propagated, and this gets communicated to the theory solver, to the Gauss-Jordan Elimination solver, the number of unknowns get closer to the rank, and eventually the Gauss-Jordan Elimination starts giving us propagations and conflicts along with the reason close, of course, hopefully. And because propagation is a lot cheaper to do in CDCL than in Gauss-Jordan Elimination, as you might imagine, it's not cubic in CDCL. We do propagation first fixed point in the SAT solver and then in the Gauss-Jordan Elimination. So we first do the part in the CDCL solver, and then we move on to the Gauss-Jordan Elimination solver, the theory solver. So what are the requirements for this Gauss-Jordan Elimination solver? Well, it must be able to produce a reason for the propagation of conflict that happens. This is really important because the reason is the clause that eventually, when it gets evaluated, given the current set of assignments, provides the propagation of conflict. And this is needed for the first UIP conflict clause generation that is a cornerstone of modern SAT solvers. It must also be able to set a variable to a value, like true or false, as the SAT solver branches on a variable or propagates a variable. And it must also be able to backtrack. So when the SAT solver conflicts or restarts, then the Gaussian elimination needs to be solver needs to be able to go back to a previous state and unset a variable. And of course, it needs to be fast. So as you can see, it needs to perform Gaussian elimination many times as we go down the search tree. It needs to be able to backtrack and go back to a previous point in time. So how did we do this? Well, we actually don't keep one matrix, but we keep two matrices. One that is an assigned matrix on the left-hand side that runs a completely normal standard Gauss-Jordan elimination. And on the right-hand side, we run what we call a reason matrix, an R matrix, which is never assigned, but mimics all the row swap and the row XOR operations on the left-hand side. So the way this works is that the two matrices are the same at the beginning of the search, because they are both at the top level of the search tree. And as we go down the search, for example, here, if you see you don't see my pointer, but the in this case, the X3 column, so if you have a look at the X3 column, is actually assigned all the way to the X3 has been assigned to true. And so the X3 column on the left-hand matrix has been all zeroed out, just like you would in a Gauss-Jordan elimination. Now we can look at this a matrix and see that, for example, X5 is propagated to 0 because the line that is just below the bottom line has a single 1 in it, and that is the X5 propagating to 0. And on the right-hand side on the matrix, you can see the same line where X3 hasn't been assigned, of course, and it's just the pure XORs that were given into the SAT solver, or in this case, the theory solver. And we can read out the reason clause for this propagation on the right-hand side. So the left-hand side is basically where we run the Gauss-Jordan elimination algorithm, and it allows us to see, a propagation, for example, that X5 is equal to 0. And on the right-hand side, we can read out the reason clause by just looking at the same row that the propagation of the conflict on the left-hand side is showing. So this is the way that we did this. Now, there are some tricks about this because, as I said, the Gaussian elimination is run on the left-hand side. But the problem is that when you want to backtrack, the left-hand side matrix will have columns zeroed out. And we need to unzero these columns, which is, of course, impossible. So because we have already lost that information. So what we do is that we actually, the way we backtrack is that we save data and information as we go down the decisions and the branching of the SAT solver, and then we can load back a previous state of the we can load back a previous state of the matrix. So we basically keep breadcrumbs of the state of the matrix as we go down or the matrices, of course, both matrices, as we go down the decisions in the SAT solver and the propagations. And eventually, when we need to backtrack or restart, then we can reload the previous state by just effectively issuing a load operation for the save state that we already saved before at every branch. And now that we have basically built this Gauss-Jordan elimination plus partial weighted MaxSAT solver, which we call Gauss MaxHS, we ran them on the challenge instances that I described, so the spin glass model and the network reliability models. And in total, there were about 9,600 benchmarks that we ran. And as you can see, Gauss MaxHS is much faster than MaxHS with top-level Gauss-Jordan elimination. So here we actually sort of cheated and gave an advantage to MaxHS, because we didn't just run pure MaxHS. We actually ran MaxHS plus Gauss-Jordan elimination at the top level. So that to demonstrate that actually running the Gauss-Jordan elimination at every state, every level of the search tree is important and provides meaningful benefits. So all both the graph and the data that you see here are with MaxSAT with top-level Gauss-Jordan Elimination. And as you can see, there are a whole set of instances that MaxSAT with top-level Gauss cannot actually solve. And also the ones that it can solve, it solves it slower than, on average, than R2 Gauss MaxSAT. So what are the conclusions? Well, first of all, if I may point you towards the actual tool, you can draw your own conclusions. You can run the tool yourself. It's online and also contains all the instances that we used. So you can rerun the experiments and try it on your own type of instances that you challenges that you have lying around. And of course, in our evaluation, it was much faster than MaxSAT with Gauss-Jordan Elimination at top level. The real-world use cases of CNN XOR in the MaxSAT domain can now be solved with ease, as we have demonstrated. So things that were impossible to solve. I mean, I guess you have seen these instances that literally were not possible to solve at all within a 5,000-second timeout, and we solved them in under a second. So there are some serious improvements that we have that this system can bring about. And I mean, finally, I think it's important to note that we actually improved on the Gauss-Jordan Elimination system that's presented in this paper with the work that we did together with Gott, Soos, and Meel. So Stefan Gott also was part of the team there, and that improved the matrix saving and loading in a way that it's no longer needed. We can actually go around this in a way that that doesn't require us to save and load. Yeah, let me know if you have any questions, and thank you so much for your time.